So dear friends, in this video we'll cover the comparison of electric and magnetic circuit, Fleming's left hand and right hand rule, and force on current carrying conductor when it is placed in the magnetic field. So let us start one by one topic. So previously we have seen the magnetic circuit, various definitions of electromagnetism, and after that we'll here cover the next topics of electromagnetism. So the comparison of electric and magnetic field, let us see in detail. So electric field, electrical circuit at one side and the magnetic circuit on the another side. Now basically when we see the electrical circuit, the basic electrical circuit will contain the battery source, which is a EMF, a conductor having a resistance R, and the current which is flowing through that conductor. So this is a simple circuit. And here in magnetic circuit, so we can consider a core. Over this core, winding is wounded. Now this winding is supplied with the current I, so that it will produce the MMM, magnetomotive force. So it will circulate the magnetic flux inside the core, which is denoted by phi, and the reluctance, which is the opposition to this flux. So when we equalize the parameters, so in electrical circuit there is a EMF, in the magnetic circuit there is MMF. In electrical circuit there is a current, in magnetic circuit there is a flux. In electrical circuit there is a resistance, and in magnetic circuit there is a reluctance. So based on this, let us see some points one by one. So in electric circuit, as I said, there is a electromotive force, the force which is responsible for the generation of the current, which is measured in volt. Now in the magnetic circuit there is an MMF, magnetomotive force, which is responsible for the generation of flux, which is measured in ampere turn. The next point is the current, which is the rate of flow of charge, unit is ampere. And similarly in magnetic circuit there is a flux, which is the number of line of force in the magnetic field, which is measured in Weber. In the electric circuit there is a resistance, which is opposition to the flow of current, measured in ohm. And in the magnetic circuit there is a reluctance, which is the opposition to the flow of flux, measured in ampere turn per Weber. EMF, which is given by current into resistance, multiplication of current and resistance, and MMF, which is a multiplication of flux and reluctance. Resistance, which is given by rho L by A, and reluctance, which is given by L by mu A, where mu is the permeability. Resistance, which is directly proportional to the length and inversely proportional to the area, and reluctance, which is directly proportional to length and inversely proportional to area, which is similar. So these are all the similarities between the electrical circuit and the magnetic circuit. Now let us one more point, the conductance, which is 1 by resistance, that is reciprocal of resistance, and here permeance, which is the reciprocal of reluctance. So these are all similarities. Now dissimilarities. Now what is exactly opposite in an electric and magnetic circuit? That is the dissimilarity. Electric current can't pass through the air, but the magnetic flux can pass through the air. So this is what the totally different in both the circuits. Second point, resistance changes with the change in the temperature of conducting media, but here reluctance doesn't change with respect to the temperature. So it doesn't depend on the temperature. Third point, energy is required for the production and maintenance of current in electric circuit. So in electric circuit current is produced by the source, and which can maintain the current. But in magnetic circuit, energy is required to produce but not to maintain it. So we can produce the magnetic field, but we cannot maintain the magnetic field. As soon as we remove the supply, there will be a residual magnetism in the magnetic circuit. The next point is electric current requires closed path for its flow, but the magnetic flux doesn't require any closed path, even if it can flow through the air also. Path for the flow of current can be defined. but path for the flow of flux cannot be defined. So these are the dissimilarities in electric and magnetic circuit. So hope you understood the similarities and dissimilarities in electrical and magnetic circuit. The next we are going to cover Fleming's left hand rule. Now what does the Fleming left hand rule suggest? If we know the direction of magnetic flux and current, then we can define the magnetic direction of force. So this is what the statement given by Fleming's left hand rule. When we held the first three fingers of left hand mutually perpendicular to each other, and if index finger points toward the magnetic field, that is this index finger, middle finger points toward the electric current, that is this middle finger, then thumb will indicate the direction of motion. So this thumb will show the direction of motion. So this left hand rule often used to find the direction of force, like in the motor, right? So this rule can be used to find the direction of force when the current carrying conductor which is placed in magnetic field, as I said. Now let us see the force on current carrying conductor when it is placed in magnetic field. Now this is very useful topic. So all the types of motor which are working on these principles, all the type of motional activity, if it is done by the electromagnetic field, so based on this topic we can find the direction of the motion of that conductor when it is placed in the magnetic field. A simple example, the electric bell which gives ting tong like sound. So this electric bell is a simple example of the force carrying conductor when it is placed in magnetic field. So let us see this topic in detail. Let us consider there is a permanent magnet N and S pole. So this permanent magnet will produce the magnetic field whose line of force always travel from N to S pole. So here we can see the dotted line, and there is another conductor which is placed in the magnetic field. So this conductor is carrying current, so it will produce the magnetic field, right? So when we apply right hand thumb rule, then the conductor which is shown by the dot convention, if current is coming towards the observer, then the direction of magnetic field will be anti-clockwise, right? So here it is the individual fields. That means the one field which is produced due to the permanent magnet NS pole, and another field which is produced by the current carrying conductor. So there are total two fields. Now let us see what will happen when there are two fields in the magnetic circuit, right? So what will happen next to it? Combined field causing a force on a conductor. Now let us see, there is a magnetic field due to permanent magnet and the magnetic field due to current carrying conductor. Now what will happen? On the downside of this conductor, what we see, both the magnetic field having the same direction, and on the upside of this conductor, what we see, both the magnetic field are exactly opposite to each other, right? So what will happen, there will be a magnetizing effect on the down of this conductor and demagnetizing effect on the up of this conductor. So magnetic field will get weakened at the top of the conductor and will be strong at the down of the conductor. So resultant, there will be a law of elasticity of this magnetic line of force, which always tends to be straight. So it will push the conductor upside, right? So this conductor will get pushed by upside direction. So this is what the force exerting on this conductor. So this is due to this two magnetic field. So what we see, we can apply this Fleming's left hand rule to find out the direction of this motion. If you don't know at which direction the conductor will move, so we can simply apply the Fleming's left hand rule. So here again I have plotted with the arrow. So this middle index finger is showing the magnetic field direction. So this is what N to S pole, magnetic field direction. The middle finger is showing towards the current which is coming towards the observer. This force will indicate the direction of force. So this is what the upward direction of force. So we can apply Fleming's left hand rule, right? Now the magnitude of this force is given by F is equal to BIL, which is measured in Newton. F is equal to BIL, where B is the flux density, I be the current, and L be the length of the conductor. So we can simply calculate the force which is exerted on the conductor. If it is the conductor is moving to the plane of perpendicular to the axis of magnetic field, then this formula is applicable. And if it is not the perpendicular to the axis of magnetic field, then we can simply multiply by sine theta, where theta is the angle of the moment of this conductor. So F is equal to BIL sine theta. So hope you understood what is the topic, force on a current carrying conductor when it is placed in the magnetic field. And then Fleming's right hand rule, the another important rule which can be used to find the direction of induced EMF, which is often used in the generators. Similarly, Fleming's left hand rule, we can define the statement. The first three fingers of right hand are held mutually perpendicular to each other. When the index finger points toward the magnetic field and thumb points toward the direction of force, then the middle finger will indicate the direction of electric current. So this is what we know here, the direction of force, motion. We know here the direction of magnetic field. Then the middle finger will show the direction of current. So this is what the Fleming's right hand rule, right, which is often used to define or get the direction of current or EMF when the conductor is placed in the magnetic field. So as I said, as an example of the generator. So thank you for watching this video. We will meet in the next video.